So if we had two black holes that were highly entangled in the right pattern of entanglement, which is certainly a physically possible state. We have no idea how we would get two black holes in such a state. And you jumped into it, and then we did some simple measurement on one side and then apply them to the other side, then it will render it traversable and it will get through. That's what follows from, equations of quantum mechanics in curved space in that situation. So in that sense, the traversable wormhole that a person can get through is possible. But the part that makes it very difficult is we don't know any way to get the initial pair of entangled black holes.
Okay, so Maria, do you want to just introduce us to what this subject is about that we're going to be talking about today?
So we are going to be talking today about work that we have been doing over the past 3.5, close to 4 years now. The work started as a consortium in the context of the Department of Energy Quantum Information Science High Energy Fundamental Physics initiative that started circa 2018. And the collaboration that we have here today, the authors of these results that we are publishing, which we believe it's notable and the community also they evaluate as notable, is on quantum communication channels for fundamental physics. This was the title of the proposal we put in 2018. And how do we tie the physics of wormholes to teleportation protocol? And it's not just the wormholes that we saw in Kip Thorne's movie Contact, although that's a good question how it is connected, but it's the step-by-step physics dynamics of wormhole phenomena that are traversable. In other words, you can throw information and it can make it through. The work was in 3 axes that we proposed. It was doing classical simulations on a classical computer of quantum effects, that is calculation of the quantum theory for wormholes, doing an experiment, that means finding a mapping of what we're discussing in fundamental quantum physics of this wormhole dynamics, mapping it into a circuit that we can put on an actual quantum machine, not on a classical machine. This is Hartmut's machine in this case, the quantum computer or the quantum processor, and in that way producing the physics of traversable wormholes and then observing it, making the measurement and observing it. And doing the same as we do with every observation, comparing the data of the observation on the actual experiment, which we call quantum experiment, to what we expect from the protocol that the theorists wrote down and the calculations that the theorists calculated, which we also did the simulations on the classical computer. And Jafferis is encapsulating all of this with a body of work of himself. And before that, there is significant body of work that we used from the theory side in order to be able to say, how do we identify a wormhole? In other words, what is the driving license of the wormhole? And does the wormhole need to be 18 or 16 to have a license, or can we make a baby wormhole? And to this end, this is important because what we have here is really in its construct and structure, a baby wormhole. And we hope that we can make also adult wormholes and toddler wormholes step by step, and that other people will take these methodologies and do that. Now, our paper in draft form is called Observation of Wormhole Dynamics in a Quantum Processor. It could be also seen as the production and observation of wormhole dynamics on a quantum processor. And on the quantum processor sounds vague, but it's very specific. It means on Hartmut's Google machine. That was an extremely important part of this work, that we actually do have a quantum processor that we can embed this process. We can produce it by design, and then we can make the measurement and observe it. And I see a hand up there. Priscilla, you have questions.
I have a question, and there's many questions, and thank you all for joining, but I have a fundamental question. Please help me. What is a wormhole?
Very good.
Good.
Let's start. Maybe we can give this to Joe Lykken. He can introduce himself and tell us about old wormholes and new wormholes.
And Maria forgot to say who she is extraordinaire. We were singing your praises before you joined. A little bit what you do, and that way we can do the that way.
I'm an experimental particle physicist, and we have been working with Jesse and Priscilla from neutrinos, which are also quantum particles, to LHC physics, to quantum teleportation, which is important also for this work. We're going to talk about that. I'm a professor at Caltech, and the past 6, 7, 8 years, I started sticking my nose on a lot of the quantum information science and engineering topics. And I'm very proud of this collaboration, this very diverse collaboration, and the results that we're putting out now. And so let's start with Joe.
Okay, I'm Joe Lykken. I'm a theorist here at Fermilab. I started our quantum program here at Fermilab about 5 years ago with the idea in my mind that hopefully we would get to the point where we could start thinking about quantum gravity with quantum technology. So that was actually my main personal motivation for getting into the whole field of quantum science. So now I'm super happy that we have. Wormholes is an old idea. The first really explicit discussion of wormholes is a 1935 paper by Einstein and his collaborator Rosen. They were interested in wormholes from the point of view of general relativity, which of course is a classical theory, so it's not quantum gravity. But they pointed out that wormholes do exist in the classical context, and they could write it down mathematically and as a simple solution to equations which are very similar to how you describe black holes. In fact, you can think of the simple Einstein-Rosen bridge, which is the simplest kind of wormhole, as you go into what looks like a black hole, and then if it were traversable, you would eventually come out what looks like another black hole. And the problem is that it's not traversable. And so the simplest wormhole, the Einstein-Rosen bridge, is you can go into it, but you can't actually come out of it. But that was a simple enough idea to get people speculating about the idea of traversable wormholes, which if you could make one, would actually have an entrance someplace and then would have an exit someplace else. And so it would be something that would exist gravitationally, but if you had a big enough one, you could travel through it without even noticing that anything was happening. And so the beauty of a traversable wormhole, if you can make one, is that it gives you a different way of getting from A to B, where you can actually survive and use it as a method of transportation. Now, of course, if I can do that for a human, I can do it for much simpler quantum systems. So if you're interested in wormholes, you don't start with people, you start with the simplest quantum systems you can think of. And that's of course what we're doing in this experiment.
And maybe this is a good segue, because I know that Priscilla is going to say, wait, from general relativity, you talk now about quantum and you talk about traversable wormholes. So Jafferis, take it.
Yes, help me. Keep helping me. This is the
And Jafferis, when you first thought of it, did you how do you even think of an experiment that you might do? Are you visualizing it as a physical thing?
I'm Daniel Jafferis. I'm a professor of physics here at Harvard University. I do quantum gravity, string theory, high energy theory, so I'm a theorist. The big questions that I would really like to understand are, what are the rules of the quantum theory of gravity in our universe? And of course, it's mostly theorists' game, because we're not able to achieve high enough energies to break space-time apart into its constituents. So the connection between the gravitational aspect and the quantum systems here is that the gravity is a kind of emergent gravity. So we have some complicated quantum system, or a strongly interacting and highly entangled quantum system. And then there's an effective description or an alternative description of the dynamics of that system that is, mathematically the same as gravity. And we could say, in some sense, it's a, very tiny emergent piece of space-time. But in these systems, if you can describe the same system using, ordinary equation of, some quantum spin system, or the same dynamics are described by something that looks gravitational. So it's kind of in the same way that, water waves are an effective description of water molecules. Here, the collective description of lots of quantum entanglement, it's sort of the simplest description of all of that dynamics is through the gravitational variables. So that's kind of where this connection comes from. And that really goes back to this thing called the idiot-CFT correspondence or holographic correspondence that's was formulated in a theoretical or mathematical sense in the late 90s by Sainer. That's kind of the original starting point. And we could kind of approach it from several directions. So, if you had a wormhole with large black holes that humans could fit through, we could interpret it from the outside as just two separate entangled black holes. And we don't often, maybe astrophysically, we don't often discuss quantum properties of black holes because it's a very fine-grained thing to ask about an enormous object like an astrophysical black hole. But in principle, if we take two astrophysical black holes and put them into a maximally entangled quantum state, if we could achieve that, we don't know how for astrophysical black holes, but if you did, then their interiors would be joined by the Einstein-Rosen bridge. So that's kind of the physical meaning of the Einstein-Rosen bridge, which was very unclear to Einstein and Rosen and many people since. Right? They weren't quite sure whether it was an artifact of the equations or not. Kind of by a funny coincidence, the same, Einstein, Rosen, and the third person, Podolsky, wrote in the same year, first paper on quantum entanglement, the EPR paper. And I don't think they would have ever dreamed that the Einstein-Rosen bridge solution of gravity had the physical interpretation of a pair of maximally entangled black holes. But that was kind of discovered over the past approximately 10, 15 years and formulated rather precisely by Sainer and Sussman. In a way, this kind of quantum experiment probing emergent gravity is like trying to build the tiniest emergent piece of space-time and probe it from the opposite direction. Of course, that kind of thing we can only send information through. We cannot send particles through our.
So maybe I can jump here. In 2018, when we were imagining the problem, constructing the problem, we did have the part of the classical simulations, the part we discussed with Google already.
Did you come together as a team, Maria? Like, how did you even meet everybody?
Yeah, hang on. First of all, I was the chair of the PAC at Fermilab, the Physics Advisory Committee at Fermilab, and I started putting quantum together with Joe in the program at Fermilab, Quantum Science and Technology for Fundamental Physics, intersections with high energy physics. We were trying to put this proposal, and I had already started quantum teleportation experiments, as you know, in 2017 with InQNet. So we were thinking, can we do an experiment, quantum optics experiment over a fiber and do the conception steps of making some more complex and tangled states on a quantum network? And that would be impossible. That was an experiment that we just had to create the simplest form of it, and it's already complex in the simplest form of it, where, for example, Samantha has been working all this past years. And then we discussed, because of the literature that appeared in the paper by Jafferis, well, we can do calculations and simulations. How about we write down that we can actually encode this, map the problem on a quantum circuit? So we talked to Jafferis, we talked to Hartmut, to Google, and Fermilab already had a collaboration with Google in the proposals because the DOE encouraged collaborations with industry. And all of us thought that this is insane. The referees of the proposal that got funded thought that I'm the PI, so they thought I was completely nuts. Jafferis said, let's do it, it's going to be fun. John Lykken said, what the heck, we can do it, but maybe not, but whatever we do, it's going to be worth it. We're going to find something out. And the students were like, yeah, we will do it. We will make it. So the collaboration was set up back then, and it was quite persistent. We pressed on it very much, and we had to do a lot of acrobatics that are results of the brilliant minds of the students that they Alexander Michael Zlokapa had some acrobatics in order to make it fit. But yes, we had the original idea written down as such, and everybody, including the referees, I think, thought this was impossible, but it was worth the shot. This is why we got funded.
So at the beginning of it, right? So Hartmut, they come to you with this idea, right? And the thing is that quantum computers, I'm not sure that they have all that same LHC rigor around them, but in order to start to make these calculations, they have to be super precise. Do you have to go through a physical process to get the quantum computer ready to take the photograph or to look at what we're testing?
It's funny that you mentioned LHC. I often think of our quantum processors as the equivalent of an LHC in the complexity direction. The LHC probes nature at very high energy scales and maybe more importantly, very small spatial scales. But our processors allow to probe nature at very high dimensions of Hilbert space and the complexity direction. So yeah, I'm Hartmut Neven. I'm the founder and lead of the Quantum AI project at Google. And what our project is about, we are what people call a full stack operations. So we build or try to build useful quantum computers, but we also build all the necessary software, the whole stack up from essentially the operating systems for quantum processors all the way to convenient to use development environment where you can formulate circuits and then run them through a cloud interface.
Now, Hartmut, a lot of times with quantum computers, you get to an answer, but you can't necessarily tell how you got to the answer. So within a project like this, Maria, is that an issue or is that not an issue?
Well, we designed the project so that we can compare also with the calculations, and Jafferis can speak to the calculations, and Joe and David and Samantha, because we run the calculations of the quantum phenomena in classical computers, and we calculated a lot of this by hand with Mathematica or what have you. So we did have spectra to compare with and variables. Just like you said at the LHC, that we have momentum of a particle, or the picture that you said. Well, so we have the equivalent of these variables that characterize the wormholes that we can compare from the calculational or classical simulation to the data that Alex embedded on Hartmut's computer, and we saw the phenomenon being observed on the circuit. So we knew everything. The question would be, would the data support what we knew from the theory that should be? Would our baby wormhole be too baby that we couldn't say if it's a baby wormhole or a baby, frog? That was the question.
Right.
Sorry for the frog.
Yeah.
It was Mandalorian, this one. And maybe Alex can say more to this. The Hartmut's machine has such good fidelity, and the engineers and the physicists there have a good description of the noise model that we were sure that we could tell San Antonio from the pig, as the people in Rome say for the cathedral there, that we would not mess it up and that we can follow because it's a circuit. In the same sense that we have circuits with transistors that use current to go back and forth, here we have a quantum circuit, and we have, for every order that we give for the quantum circuit to calculate, including the entanglement as a resource, if you want, or as a current, we know what to expect. We can calculate it. And so this is, for us, it's not a black box.
Right.
So maybe Hartmut wants to say something more, and then perhaps Alex can say a few things.
So what I find fascinating about this experiment, and why do we build quantum computers or quantum processors in the first place? I mean, there are various known applications for those, but one very attractive one, we often refer to it as Feynman's killer app. Richard Feynman, of course, the famous Nobel Prize winning physicist, was the first to realize the, in a way, rather straightforward insight that, hey, a quantum processor or a quantum computer should be rather good at simulating systems where quantum effects play a role. And indeed, this is something we now routinely do. We study states of matter, ideally very exotic states of matter that are otherwise not easily accessible to experiment in a lab. And you may have seen last year we did something called time crystals. It's an example for an exotic state of matter, but I feel the traversable wormhole takes this further. And the fascinating thing is that it's a true experiment, in the sense that it wasn't exactly sort of the clean textbook equations that you would use for describing a traversable wormhole, because to integrate those or to simulate that system on a quantum processor is still too expensive for the machines we have today. We don't have that many qubits. We don't have the high fidelity that allows us to run that many gate operations to truly couple, let's say, two wormholes described by the SYK model. So Alex had to go through a process to simplify this model and to sparsify, to thin it out. And on the one hand, this was just necessary to make the experiment work with the quantum resources we have. But there is a very interesting, deeper upshot to it. It shows that these ideas about holographic duality are robust, because the physics was still there. And that's not completely clear, absent of an experiment, that this would be true. So we develop a little bit more confidence in these basic ideas that they could indeed describe nature in a faithful way.
So yes, and let's segue to Alex, and he will tell us how from a monster Hamiltonian that would need all the monstrous quantum resources that nobody had, how did we arrive to the baby Hamiltonian that we could put on Hartmut's baby, which is his Sycamore computer.
That's very my baby. I think I feel embarrassed for my team.
I know, but it is your baby though. Now it's ours too. This is the thing.
Hello, I'm Alexander Zlokapa. I was an undergraduate student at Caltech studying physics, and now I'm doing my PhD at MIT over here in the Center for Theoretical Physics. I guess my main interests lie in both quantum computing and machine learning, and this project kind of surprisingly unified the two interests as we tried to find a wormhole that we can actually realize on a quantum computer today. So the key insight was to in artificial intelligence, people always work with neural networks a lot. And there are a vast literature of ideas that go into how do you train a neural network well. Meanwhile, in physics, we usually use pencil and paper to try to derive what is a good model of a wormhole, something that has properties that we can consider to be gravitational. And to be able to run on a quantum computer we have today, we need to use a very small system. And so to obtain a small system, we had to take the two ideas from those training ideas used in neural networks and the wormhole physics that we've done with pencil and paper and really marry the two. Basically meaning you write down your wormhole as a neural network. You train it as if it's a neural network, completely oblivious to the fact that there's any physics involved, except that you ask it to preserve some of the wormhole properties that you know should exist. And so the machine learning discovered how to make the simplest possible model of a wormhole. Something so simple that we could run it on today's quantum hardware while still observing the full spectrum and the rich features of what you would expect from a wormhole.
And the question is, of course, this is one of the points, Jesse and Priscilla, that if we didn't have the machine learning, would any one human be able to arrive to this Hamiltonian? And the answer is probably yes, but would it take as long as we took? The answer is probably not. In other words, you could sit down and write the physics with very few terms without the machine learning, but the machine these methodologies, and it's not the way it was used. It was an extremely clever way. So it wasn't blindly, it was in a very extremely genius way that Alex did this, so that we preserve the physics of the wormhole dynamics in one variable, and then we check that they reproduce it in the other variable. So there's a lot of physics, and just the machine learning blindly would not do it alone, and just the calculation blindly would take a much longer time to fit it in this architecture that we have, Hartmut's architecture.
Now, is that standard computation? You're doing that on regular computers, and then you get to a certain point and you give it to the quantum computer, or is it just on the quantum computer?
Yes, so the artificial intelligence is run on a classic computer first. We're using the full machinery. In fact, we wrote it exactly the same way as you write a neural network on a classic computer. And then it comes out with a physical system and says, this might be a wormhole, and we know it preserves some property. And then we take that system and we run it on a quantum computer, and we can actually directly measure things like if we throw a qubit through one side of the wormhole, and we measure if it came out on the other side. And we check how often that happens. So this is something that we can then take and actually run on the quantum computer.
I have a quick question for you, which is, in your determining what are those principles or whatever coding or whatever it was that would create a wormhole, how do you even get to that place? Because if no one's ever done it before, how are you getting there to determine what those elements are to feed into the machine?
So we actually, there's some stuff we knew and some stuff we learned. And that's the fact that we learned new things about wormholes in some sense is, I think, exciting. So we know, for instance, that you need to be able to prop up a wormhole with a negative energy shock. And so we can turn this a negative energy shock on or off and check if this thing is going through the wormhole or not. And if you turn it off, you shouldn't get anything going through the wormhole. That's like the basic check that our neural network was looking for in developing a new physical system.
In other words, we do know the physics, and we can check it as we construct the whole machinery, the mathematical or the algorithmic machinery of how to sparsify, on how to make it really small so that we can embed it. But we know the physics. Like Alex said, we could test the physics as we are implementing. And I'm pretty sure that if we didn't do the training correct and we departed from the physics, we would have observed it, that now we don't have a wormhole phenomenon.
But there's something also exciting that we learned in that a couple of years ago, a team from Stanford proposed one underlying mechanism of wormhole teleportation that they argued was likely kind of a key gravitational feature and had some examples of evidence. And it makes it very tricky. Essentially, imagine you had like a tray and you put a bunch of coins on it and they're all heads up. This is like a single qubit that's fully coherent that you're about to throw in the wormhole. As it goes through the wormhole, you shake the tray and your coins, some flip up or down, it's all mixed. But by the time the qubit goes to the other end of the wormhole, you keep shaking the tray, they all flip back to heads. And that's like a remarkable property that's very special. But the fact that wormhole physics forces this to happen was proposed by the Stanford team.
Yes, this was the shuffling mystery that it looks like some magic has happened. It's,
yeah, yes, and thank you for that analogy, Alexander, because all of you know what you're talking about, and the rest of us watching need these, even if they're just sort of banal, analogies to sort of try to understand something that is really incomprehensible to most people, that you all live this every day. So thank you. Whenever any of you have an analogy, like the coins going back, please throw them at me.
So did the Stanford's group, did their ideas, were they consistent with what you found when you actually did the experiment?
Yes, so that is actually the very surprising thing. The AI didn't know about the Stanford team proposal. It was just looking for this basic measure of, if you prop open the wormhole, will it allow things to go through? And so we trained it only with this basic thing. And the model that it returned is this small system. We checked to see if it has this Stanford's proposal of what a wormhole does. And it basically perfectly fit the Stanford hypothesis, which was quite surprising. But it also offers very good evidence for like a deeper understanding of how this works.
Yeah, and maybe David can say something more on that, since he was part of the extended Stanford proposal that gave some of the characteristics of the wormhole, that includes the size or momentum of the, let's say, wormhole and this kind of characteristics. And David maybe he can introduce himself and tell us a little bit about his work.
Great. Yeah. Hi. Thanks. Yeah, so my name's David Kolchmeyer. I'm a graduate student at Harvard, graduate student of Daniel. And yeah, so this mechanism of size winding was proposed by this group at Stanford. And basically, the idea, well, let's see, I guess there are different ways to think about it, but one way to think about it is to kind of identify how we can think of quantities like momentum in the gravitational theory in terms of quantities in like the quantum mechanical theory and the SYK model. And there's some explicit formulas for how that's done in some papers, including the Stanford paper, I guess using these ideas of how we relate momentum in gravity to some analogous quantity in quantum mechanics. The Stanford group had an idea for what the specific mechanism is that underlies this wormhole physics. So in other words, they proposed that if you evolve an operator and you look at its, well, the quote unquote size distribution of an operator, just meaning how many qubits is this operator actually acting on. This distribution is analogous in some ways to the distribution of the position of a particle in the gravitational space-time. And so by making this analogy, they were able to predict that this kind of way that the operators evolve in the quantum mechanical theory is responsible for how the quantum teleportation actually works. And they demonstrated this explicitly in this very standard model, the SYK model that we use a lot in theory. And so I think something that's really remarkable is the fact that even in a much simpler, smaller model, the model that we looked at compared to the SYK model, this notion of size winding is still there. And in the paper that the Stanford people wrote, they tried out many different systems, not only the SYK model, but other systems too. And the other systems were maybe simpler and didn't have size winding. So I think it's pretty cool that we were, I guess, able to find a system that actually obeys size winding and isn't exactly the SYK model, but is rather something much simpler. And I think the underlying reason why our smaller system actually obeys size winding, I think is still something that's unclear, but is very interesting and should be investigated further.
When we say size winding, is that like the in genomics, the shape of the particle as it goes through? Is it that it has a corkscrew shape as it goes through, or am I not understanding what you're saying by side winding?
Well, I mean, it's not the shape in physical space, but it is something, it's a characterization of what your original qubit evolved into. So we kind of inject into the system a qubit. So we send a qubit into the system, and then it starts to interact with the rest of it. That's really what the quantum computation is. You can think of it as a kind of, we sort of realize in the quantum computer a physical system, and the dynamics of that system starts to mix all of the qubits together. That's what the analogy that Alex mentioned was about with the coins flipping. Those are like the qubits, the kind of, so an original qubit is single one, and then it starts to grow and be a combination of many qubits together.
Right.
And the size winding is the terminology to refer to a particular aspect or shape, so to speak, in this generalized or abstract sense of, the way in which the qubit is encoded now among many qubits. So it's characterizes something about that.
Yeah, but and let me jump. The emergence of this direction where the bridge is coming, like you called it with a screw, perhaps we can make an analogy. That could be an analogy that there is an emergence of space through which the qubit goes, and the size winding could characterize that.
So the amazing part here is that the qubit goes through, it goes through some system, and then it comes out the other side in the same way that it went in. Yeah.
Yeah,
Right, exactly.
But in the middle, it goes through
In
this
the middle,
chaotic
it's
regime.
very scrambled. So you kind of, there are like two reference frames to describe the system. One of them is the lab frame, where we think of the thing as a qubit system. Then we inject some, single qubit, the dynamics of the quantum processor starts to mix it. It becomes a very complicated combination of many qubits. We do some operation, and then it re-simplifies in the other side of the system until it comes back to a single qubit now on the other side of the system. And then the other description is, if you like, what it looks like from the point of view of the qubit. And from the point of view of the qubit, it experiences this emergent gravitational space-time in which it simply travels through causally from one side to the other. So in a way, the Stanford paper was an attempt to describe, if you have a quantum system for whose internal description looks like a wormhole with something able to traverse that, what is the property in the language of the qubit that will correspond to that? So a particular form of the way the qubit eventually gets encoded or scrambled into the system. That's what that was about. And we optimized or learned a kind of system that will make the signal that we were looking for strong. We didn't input that it would obey the mechanism in the qubit language of the Stanford paper, but amazingly, it did. So it's kind of, it shows that really was the right way to characterize what you need to have in the qubit language to make the gravitational description, work. Work meaning that it looks in the gravitational side like something traveling, causally through the wormhole.
Maybe at this point, maybe a good place to inject what I think is a rather important sentence or a comment. Namely, I think it's probably correct to say that what we're looking at here is the first experimental data that finds its most concise explanation in terms of string theory. Because you could just look at what Daniel described as a lab frame, essentially the quantum circuit, and there it's not completely clear why this should happen, that the information of the qubits that you swap in on the left comes nicely out at some point in time on the right. Sure, you can follow the constructive and destructive interference of the different waves, but that is a very clumsy explanation. It's essentially just describing in words what the circuit does, versus in the language of quantum gravity or holographic duality, said, no, of course, this had to happen because we threw a qubit into a traversable wormhole and plop, there it comes out on the other side. I think that's an exciting thing to happen, that the language of string theory gives us the best explanation for this experimental data.
Yeah, maybe we should say this in the beginning, in the middle, and in the end, because that's a very good, that's a very exciting, and I think that's why also Daniel was very excited to write the protocol. But maybe we can ask here something about teleportation, and maybe because this is teleportation protocol, but not the kind of teleportation protocols that we run on the fiber systems. So maybe Nikolai and Samantha can tell us a little bit about what is teleportation, and then we can ask the question, how is this teleportation, the wormhole teleportation, different than that? So Samantha, you want to start?
Sure. Yeah, I can take the first part. So my name is Samantha Davis. I'm a second year graduate student at Caltech in physics. I do experimental work and theory in mostly quantum communication and quantum networks. I was part of the team that did the long distance quantum teleportation demonstration at Caltech and Fermilab. For this project in particular, I was mostly involved with the simulations of the wormhole protocol on the classical computer. And it's very exciting to see the connection between this kind of teleportation that I mostly do in the lab versus this kind of wormhole version that we're doing. So we can think of quantum teleportation, at least for a communication application, as, let's say that you have Alice and Bob, and you want to send a qubit between them. So encode some message in quantum information. There's a number of proposed benefits for this. For example, like high security communication that you can do classically. So let's say that we have this qubit at Alice and we want to send it to Bob. So we first create a pair of entangled particles, and we introduce this person here, Charlie, in between Alice and Bob. And so we share this entanglement between Charlie and Bob. So we have entangled photons here, for example. With this pair of photons, we then interfere Alice's photon or qubit and do a quantum measurement here called a Bell state measurement. And then by performing this quantum measurement, you've essentially transferred the information from Alice to the photon that's at Bob. So in doing this, you've sent a qubit over some distance without physically sending Alice's qubit the whole way to Bob.
Right.
So here you can use this for a number of applications, for example, quantum like internet applications. So for example, if you want to link multiple quantum computers over long distance, and this benefit of being able to send this qubit not the entire way comes up because it's very hard to send a qubit over long distances without it interacting with the environment. Mm-hmm. So by having this person, Charlie, at the center, you can send Alice's qubit over twice the distance with only having her sent it, half of the way.
So is this, you think that this particular technology can end up linking distant quantum computers? Is that one of the applications?
That's one of the main applications for this. I think maybe Nikolai could expand more.
Yeah, Nikolai can talk to us a little more, and then we can ask the question, how is the wormhole teleportation protocol? How can we use it if we can use it in the future? And Joe has thought about this, and Daniel has thought about it, and all of us, but maybe Nikolai can introduce himself, tell us a little more about why teleportation is not superluminal or anything like that, so that we avoid the sci-fi story here.
Yeah. Hello, everyone. My name is Nikolai Lauk. I am a postdoctoral researcher with Maria, now like third year already. And I'm mainly working on the photonic teleportation, or like, let's call it conventional teleportation nowadays. And also quantum networks protocols and quantum networks design. So what Sam mentioned, that in order to perform the teleportation, we need to do Bell state measurement. But one important part of this is that it's not sufficient to do the Bell state measurement to teleport the qubit. We also have to communicate the outcome of this measurement to the Bob. That means there is still required a classical way of communication. And because the fastest that we can communicate is the speed of light, that means there is no superluminal information transfer whatsoever.
That means there'll be no time travel?
Exactly, there's no time travel.
No time machines.
No
Yeah.
time.
Right, because if I do not communicate, like the bulb will look at this qubit and it like will measure a random. So the bulb would not be able to extract any information out of the previous qubit that Alice possessed. And for the wormhole teleportation, we have similar thing, right? So we heard already like that in order to do the wormhole traversable, right, we have to send the negative energy pulses, right? And on the quantum field theory side of the things, it is done by enabling communication between these two asymptotic quantum fields, and they should be interacting with each other, right? So at the same time, so that means that the information has to travel, and in that sense, also like our wormhole teleportation does not allow any time travel.
Mm-hmm. And the difference in the one case from the other case is that in the wormhole, in the protocol that Jafferis wrote, we can clearly say that there is emergent space. In the normal teleportation, there is no emergent space. Maybe Joe or Daniel can say a little more about the difference.
Yeah, I mean, well, maybe just to kind of give a slightly different angle on the whole story. I mean, if we started by thinking about quantum teleportation, I mean, one way to understand quantum teleportation is that it's the quantum version of shared key cryptography. You want to send a piece of information, but instead of sending it directly, you compare it to a reference. And then the thing you send is whether it's the same or different than the reference. That's what you do in classical shared key cryptography. Here it's slightly more subtle because you want to send a whole quantum bit, which contains, not just the 0, 1, but it has some amplitude to be 0 and some amplitude to be 1. The comparison is done toward half of a quantum entangled pair. That's like the key. But the information that's sent is just 2 ordinary bits. So somehow by sending 2 ordinary bits, the entire qubit gets communicated. And, of course, we perfectly understand how it works from the rules of quantum mechanics. It might seem a little surprising from the point of view of the qubit. So if you imagine that, we quantum teleported a person by comparing all of their qubits, however many define a person, an enormous number, right, to an entangled collection of the same number, and how would the person, feel like they got to the other side? It sounds a little bit hard to understand. And I think one of the amazing things about the holographic duality in this case and the description with emergent space-time is that at least for some version of this protocol, which is perhaps a little bit more complicated than the standard teleportation, there is a causal description from the point of view of the qubit being sent, where it feels like it travels through the emergent wormhole. And if we just had the entangled pairs, but you didn't have the direct communication, then the wormhole will never be traversable. And you will jump into it and die in the interior. That better be, because you shouldn't be able to use just entanglement to send signals. That would be superluminal. And it's the protocol itself. It's the fact that you make the measurement on Alice's side, tell the answer in classical information to Bob, and then Bob does some operation on his side. When you go from the point of view of the emergent space-time, your qubit is inside the Einstein-Rosen bridge. And then the operation that Bob does sends a pulse in, and this pulse has a negative energy, and this negative energy pulse, which is generated by the protocol, is exactly what opens the wormhole up and allows the qubit to get through. So it's kind of an amazing correspondence or agreement between these ingredients in the language of a quantum system and teleportation and the description in this gravitational situation, because people also in gravity wondered, could you have traversable wormholes? And they, knew that they needed negative energy. And there are, general results that tell us that kind of negative energy pulse is not possible unless you make a direct connection between the two sides. That's basically what prohibits wormholes from becoming time machines. So these things kind of fit together in an amazing way.
So the qubit that I send through, is it exactly the same qubit on the other side?
So we usually identify qubits by their quantum information content. And that leads to a unique identity because of a very important difference between classical and quantum information, which is that classical information can be replicated. So you can't identify a unique copy of something with classical information, right? That's why digital copyright is such a fraught and challenging topic, because for you to copy something that doesn't destroy the original, it's physically possible, right? But quantum information is not like that. The basic rules of quantum mechanics, like the linearity of quantum mechanics, implies that it's not possible to start with one qubit and just replicate this qubit. So quantum information has a kind of unique identity that you can track through its evolution in a system. Now, of course, it may be that your original qubit gets scrambled into a very complex combination of properties. So in practice, you may lose the qubit. You can never duplicate it, but in practice, you could lose it. But the interesting thing here is that these are setups where first it looks like it's being scrambled into a very complex property, but then the protocol manages to unscramble it so you can extract it again, and then ask, what is the pattern of, when should you look at the system to extract it? That's kind of the pattern of when the signal emerges. And then that's the kind of pattern that we compare to the emergent gravitational description. And, as Hartmut said, it's quite amazing that, this is a situation where, the gravitational description is the simplest way to think about why the pattern of this signal looks the way it looks.
Can I ask a question around what goes through, what distinguishes it from classical, though, when it comes out, is it the same? And somehow it went through that extraordinary process of untangling it, coming back in together, and it's happening in with no time. I mean, time stop. I mean, it goes in, it gets thrown out, and what the implications of communications is what I'm starting to see that probably never done before. Because what you're really talking about is this unbelievable communication inside that is, throwing the thing out, and it's the same. I mean, that's where everyone in science fiction and things, you get this thing about something going through the wormhole and they come out and they're the same. But is it the same, or has it somehow been deified or changed in some way?
Yeah, it's an interesting question, Priscilla. So, I would say that the same here is defined by the information content. That's kind of the only notion of same that makes sense, say, for fundamental particles, right? Well, all electrons, any electron is equivalent to any other electron. They're distinguished by what quantum state the electron is in. So it's same here in that sense. Of course, the whole point is that the pattern of the qubit started in one place, and that pattern ends up in another place. Obviously, those two places aren't supposed to be the same place, otherwise it won't have sent anything. So in that sense, it's residing in a different physical part of the quantum computer, but that's the point. Otherwise, you won't have moved the information, it would just be stationary, right? So we're kind of identifying the qubit by its information content. That is its identity here.
I can add from the kind of normal teleportation perspective. So back to when I was saying that, you know, we have Alice, we have Bob, and we share this entanglement. So the idea is that, so let's say that we have a photon that we encoded this qubit into. So when we perform this measurement, we destroy basically that quantum state, like we measured that state. But because of this entanglement that's shared through, and the combination by sending the result of this measurement to Bob, the information that was at Alice appears at Bob, essentially.
Reconstructed. It's reconstructed.
Right. It's reconstructed. Yeah. So basically, by doing this measurement, you destroy Alice and Charlie's qubits, but you still have Bob's. And by knowing the results of this measurement, you can reconstruct the state. And because it's basically identical in every way to what Alice was, we say basically that Alice's qubit has been teleported. And so it's this combination of this entanglement and this classical communication, which is also, you know, the reason why it's not super nominal.
Yeah, but Priscilla is on something here when she said communication. There's something about the communication here, the communication channel. And we've been thinking about that in terms of how protected is the quantum information that the qubit carries when it falls into the wormhole. And I think we have been thinking about it, all of us. Maybe Joe can say a word, because somebody will ask, well, what are you going to do with this? Okay, you will understand quantum gravity, that will be Hartmut, but somebody else will want to do something with this. Joe, you want to say a word on that?
Yeah, I mean, it's even if I don't care about wormholes, this is a new kind of teleportation. And you can ask, you know, is it good for something? We are working very hard now at Fermilab and other labs to try to understand whether we can set up a quantum internet and connect the whole world with quantum communications. And if that'll be a big revolution if we do it. But it's not at all clear what's the best way to do that and what are the advantages of using different kinds of teleportation approaches. So I think this is something we want to experiment with further to understand what really is different about wormhole teleportation, and therefore what the advantages might be in a practical system. And I think that's the kind of thing that could unfold over the next few years using the technologies that we're developing and improving on at places like Google.
You know, Joe, is this a fundamental discovery about the way the world works? Is there something fundamental underneath this that wasn't expected?
Huh.
I think it was expected, but it certainly is fundamental, because this is an example of emergent space. You know, it really goes back to this idea we've been talking about since Einstein, that you can think of space and time as some kind of fabric. And Einstein said the curvature of that fabric you should think of as the force of gravity. But you can also ask the question, what is the fabric itself? What's the weave? What's the thread that holds it together? And much more recently, we think the key to understanding that is quantum entanglement, that quantum entanglement is the thread that holds space and maybe even time together. And that's something that's really fundamental and really new. And we're starting to explore it now in this emergent way, where in some sense, we're starting to sew together a little bit of space in these kinds of experiments. And what the wormhole is doing for us there is it's giving us something we can measure and recognize as being emergent space, because the wormhole has very characteristic properties.
And does that mean that the nature of the universe is quantum, you know, at its core?
This I think is perhaps the most interesting question as to what really is the universe made out of. We've spent the last 100 years saying it was made out of particles, and then maybe it was made out of strings. But I think this is really pushing more in the direction that it's made out of quantum information, that the most fundamental thing you should think about in the universe is quantum information.
And people have been thinking about it. And in fact, there is an EAT from qubit collaboration. The theorists, both high-energy physicists and quantum information theorists, they've been talking about that, and they're creating bridges in the language. There have been people who say that the universe is a quantum computer or information or quantum information. So with this kind of experiments, we're going to start shedding light. And instead of having this kind of vague ruminations, we will put it in some sort of an experimental table and see what we can produce in terms of space or space-time and dynamics of this kind of phenomena, and what we can observe.
Yeah, I mean, maybe just to expand on that a little bit, I think our best guess for, you know, what the fabric of space-time in our universe is made of is that it is constructed out of the same kind of emergent space-time from the patterns of quantum entanglement in some degrees of freedom, whose precise nature we don't yet understand, but it is built by the same mechanisms as the emergent wormhole that we produced in the quantum experiment was built out of those very small degrees of freedom, the small number of qubits in the Google quantum machine. So the universe builds its space-time out of its much bigger collection of some quantum variables.
Hartmut, relative to traditional computers, we have very few quantum computers, even, we have very few chips, and there's going to be more and more every day. They're going to be more refined. They're going to be better. I'm sure you're actually working on that. When you look down the road, you say 5 years, 10 years, 20 years, or 100 years, what do you see as the future of this? We've experimented now in this very small area of it, but what are the next stages to explore our universe with quantum computers?
Yeah, if I just look backwards, which is of course safer than to predict forward 100 years, even though I was just last week at South by Southwest opening the track that was called the year in 2050. So I had to answer your question halfway down the road.
Did somebody else pick it up the other half, or did you just do the halfway?
No, we were only tasked to go to 2050. Yeah. Going just backwards, and quantum information or quantum computing as a field is just a few decades old. And if we looked early on what we thought the killer apps would be, we thought, it would be quantum enhanced optimization, for example. And now we realize not so fast. Yes, there will be speed ups there, but they are only quadratic speed ups. So the difference between a classical algorithm and a quantum algorithm, the number of steps you need is only reduced quadratically. And that is unfortunately not enough, because quantum error correction is so expensive that this advantage gets eaten up. This is an example where we thought we had something and then it evaporated. It may come back. So there may be optimization problems where we can get better than quadratic speed up. But now looking forward, or sort of staying with the backward part, would have ever expected that we would study the properties of time crystals, or that we would study the properties of a traversable wormhole already at this year on our chips. You would have asked me 5 years ago, I would have never predicted even that relative short distance in the future. There's a colleague of us, Jeremy O'Brien, the CEO of PsyQuantum, and he has this line that fits, I think, our endeavor here really well. He said, I do not know whether warp drives exist or can exist, but if you were to task me to build one, I would very much appreciate having a quantum computer as a tool to design it. I mean, we are almost doing or something pretty close. So I do think, and we mentioned it earlier, that this Feynman killer app of using quantum processors to simulate quantum systems, and the whole story here seems to imply or lend more credence and evidence to the fact that thinking of the fabric that makes up the universe as a bunch of qubits that interact with each other, if that's the right picture, then a quantum processor is just the tool of choice, or the only good tool we have to study this fabric of entangled qubits, and hence study and probe and investigate interesting states of matter. And that will just lead to all sorts of interesting technical devices we can use, whether it's a warp drive at the end of the day, we don't know yet, but exciting stuff is likely to come out of that type of work.
Do we think that one day a coffee cup will go through? That you could put a coffee cup down and it'll come through the other side with a piping hot coffee at the same way I put it in?
Oh, sure. That's what Keep did this. Keep sent Jodie Foster like that.
Well, so. I understand. Well, that's what I'm getting at, is that, what are we thinking? Would a human being eventually go through a wormhole?
Well, exactly. We have a baby wormhole, but eventually once we get the baby.
Well, would it, Maria? Would it?
Well, this is the kind of thing that Kip was writing many years ago, and I have the quote in front of me. One could imagine an exceedingly advanced civilization pulling a wormhole out of this sub-microscopic quantum mechanical space-time foam and enlarging it and moving its openings around the universe until it has assumed the size, shape, and location required for some specific interstellar travel project. I do believe that there are people who have this kind of projects and they're funding them as well. So the answer is I don't know, but certainly we will try, just like Jeremy will try. And I think in Contact, to mention it again, they did say that the aliens said, we didn't create this. Somebody even more advanced than us did, but we're using it. So we'll see. We'll see.
And maybe to say a few other words on that. I mean, if we had the Einstein-Rosen bridge configuration of two black holes, so if we had two black holes that were highly entangled in the right pattern of entanglement, which is certainly a physically possible state. We have no idea how we would get two black holes in such a state. Right, we can't manipulate black holes very well, and we absolutely have no idea how to manipulate them at a quantum mechanical level, fine-grained quantum mechanical level. But if you had that state and you jumped into it, and then we did some simple measurement on one side, well, enough measurements equal to the information content of U, which might be more than one measurement, presumably, and then apply them to the other side, then it will render it traversable, and it will get through. That's what follows from equations of quantum mechanics in curved space in that situation. So in that sense, the traversable wormhole that a person can get through is possible. But the part that makes it very difficult is we don't know any way to get the initial pair of entangled black holes. So but you could imagine, like a small number of entangled particles. You can imagine adding more and more particles, and maybe eventually you collapse all of your particles into black holes. And I mean, it's not completely clear whether there's kind of a continuous smooth connection between the type of emergent wormholes that we can make with small number of qubits and the physical space wormhole that a person could jump through. As you imagine, increasing your system from small number of qubits to a black hole. It's not completely clear whether that's sort of smoothly connected or not, but it certainly could be.
And the definition of what Priscilla asked, is it going to be the same Priscilla that I throw in that comes out the same and same?
Now Priscilla has to go through. You're not going to go.
I'm going. Okay, I'm going to go.
No. I just want to say, before this conversation, I wouldn't go through.
Yeah.
But now, as you're talking,
you're not going through, Priscilla.
About maybe going through.
Yes, but yeah, the definition of is it the same Priscilla that went in that comes out, it will look the same, but it will be the same in the quantum mechanical sense. Okay.
But I think
Right.
there's like this mantra in a way of information is physical, and this is definitionally true in quantum information, because if you imagine taking the entire quantum state of a person, of every single particle in their body, and then like destroying it but reconstructing it elsewhere, well, that reconstructed person will have the same memories, the same everything, because you've encapsulated literally all the information that exists about this person and put it.
But how do you encapsulate the memory?
Well, because it's part of the information.
Right. Your memories are contained in your brain. Your brain is now fully reconstructed. So
I don't know about your subconscious though, and your consciousness. If it goes, then we need to talk to Christoph Koch and Christoph Simon and people who are and Hartmut, in fact, because he's talking about quantum consciousness. If that's part of it, then you might come out really the same.
I think actually,
what is quantum consciousness? Is that a thing?
Let me say something simpler before just comments you could use. A good way to summarize it: in quantum mechanics, you don't have copy and paste; you only have cut and paste. That's maybe a good way to summarize the result of the non-cloning theorem. And you asked it numerous times: is it the same? Is it the same? I think maybe our physicist colleagues can help me to judge whether that's an appropriate analogy, but I think it is. When there's, let's say, a wave of a certain shape crossing here the Santa Monica Bay, it's the same wave, but obviously we know it's 100 meters further away, then it's different water molecules that make it up. When we talk about that entity. I think it's the same in that sense. It's obviously there's a qubit itself, there's the aluminum that makes up the superconducting islands on the left and the right sides. These are different things. I can rip this off or rip the other piece off. So in that sense, it's not the same, but the information expressed is the same, or at least in the experiment nearly the same.
You know, Daniel, what were you going to say?
Oh, yeah. Well, I think actually this setup, which relates teleportation to travel through wormholes, actually gives kind of the answer to this question of whether it's the same or not. So if we imagine doing a teleportation operation on a person, so then on the other side comes the complete copy. And you might ask, is it the same or not, as they're asking, right? I think the intuitive notion of it being the same really means that from the point of view of the person, there was some causal path. They had an experience of how they got from the starting point to the end point, right? The thing that makes one feel, like it's not very clear whether in teleportation it's a kind of copy paste or cut and paste, or if it's really the same, is that the usual description lacks a kind of causal path from the person from the beginning to the end, right? They got, some classical measurement was done, and then some classical information was sent, and somehow this quantum state is reconstructed, but it doesn't sound like it had a causal path. But the amazing part is that if you actually wanted to do teleportation on a person, of course, I could do it by compressing the data of a person and sending only a compressed version. Of course, that's not going to feel like it's the same, right? That's the same as if I took a photograph of you and sent the photograph and then they built a bad copy. But if we really want to send the full quantum information of the whole region, that means not just where all the particles are, but like the exact quantum gravity state that encodes the person sitting in a region of space-time. Then you need an enormous amount of information, which is the information of any, of a region of space-time. So you need your resource of entanglement to be two entangled black holes. Then it will feel like to the person who you sent through that they travel through this wormhole. They do get a causal connection between where they started and where they came out. So from the outside, we could say the person being teleported just got thrown into a black hole and destroyed. We measured some things outside this black hole. Because the black hole was entangled with another one, we replicated the quantum state of the person on the other side. That would be one valid way of describing it. But from the point of view of the person being sent in this situation, they will feel like they just smoothly travel through this wormhole. They will be absolutely sure that it's the same person because they have a causal history that connects.
Wait, I have a question though. What happened to the person at this end?
They jumped into the black hole and they were tossed.
Oh, they're gone.
They're gone.
They jumped in or
No,
they were thrown.
Hartmut said they're not
They
gone.
were thrown in.
Depending on how willing they were, I guess.
Yeah.
And without going into any, this is a whole different discussion we should not get into. You asked about quantum consciousness, but if you make sort of the basic assumption, what Christoph Koch would call that there is a physical correlate of consciousness, meaning there is a material, physical substrate that houses conscious experience, then if you were to do what we just explained with our protocol, this physical correlate of consciousness would make it through. So the person would, it's a faithful, not copy, it's a faithful reconstruction at a different point in space-time in the bulk language of the object that went into the wormhole.
Sam, you talked about this idea that you're going to go through, there's somebody in the middle, and then it gets replicated on the other side and it's halfway. Is it necessary within this idea that the person who goes halfway has to be destroyed before you get them to the other part? Why does he have to disappear between the two black holes?
So yeah, I should clarify that what I was describing was the kind of conventional teleportation, which is the kind of optimal architecture if you want to do this sort of long distance communication for the sake of just encoding information and sending things. And this is analogous to the wormhole teleportation, but as we described, it's a little bit different.
Okay.
But in this case, but I guess the kind of, even if you like didn't have this middle person, the kind of key thing is that you need this entanglement and you need to perform this sort of measurement, which I guess kind of maps to essentially going through the wormhole in this sense. In the conventional way, we need this kind of destruction because, as Hartmut said, you can't have a copy. You need to you're basically cutting and pasting. So you're not going to end up with two qubits that have the same state. You're going to have by doing this measurement, the state or basically the information, which we're kind of equivalent to the state, is going to end up on this other side. You don't have another like the same one here.
So this is an amazing project you guys have worked on. Where does it go from here? Maria,
many places. So first of all, like we said, this is the baby Hamiltonian, the optimized baby Hamiltonian. I think this is a step for people to start thinking about using the quantum processor for bigger quantum gravity experiment as the processor is becoming more powerful.
Oh, is it Hartmut going to let some of those out of the lab so just people at the local stores can buy them? And
yeah, he's going to let someone come to our labs and we're gonna play with them if Hartmut lets us.
I can get one down at my Radio Shack, my old Radio Shack.
And we are going to be doing many more tests with this kind of designer Hamiltonians like Alex described. We're going to be making a lot more tests on what we can run on the chip as is in terms of other quantum gravity phenomena. I think it will give an impetus of people. A lot of people will criticize us and will try to reproduce us, which is good, or find a better way of doing what we've done. So I think this will be causing a lot of insights and a lot of thinking and a lot of people from different disciplines coming together, namely quantum computing, quantum information, string theory, other quantum sensing, people from industry as well, machine learning, a lot of various algorithms, a lot of various different disciplines will come and melt together. There will be a rich set of results that one can actually derive with these new insights and these new methodologies. Also communications, like you guys mentioned, like Priscilla mentioned, quantum communications for all sorts of different kind of ideas that can be implemented.
Joe, as you look at neutrinos and you look at all these different kinds of experiments that are happening, all these different kind of scientific areas, probes, different things, like, does this change the game on all of that? Does this have to now be added into the rich tapestry of experiments that we're doing in physics?
Well, to circle back to the original Einstein-Rosen paper of 1935, the reason they were talking about wormholes is because they were trying to explain neutrinos. They thought that maybe neutrinos were wormholes.
Yes.
And it's not such a crazy idea because, again, we don't really understand the idea of elementary particles, what that really means at a quantum level. And so maybe Einstein really was onto something there in his original paper. But part of what we're doing here, we talk about the wormholes being babies, but there's a big advantage to that if what you're really interested in is the quantum part of quantum gravity. If we were lucky enough to have a black hole in our solar system the size of the Earth, we would, of course, go visit it and try to study it. But it'd be very hard to study its quantum properties because, for example, a black hole that big doesn't produce enough Hawking radiation to detect. And you can think of Hawking radiation as sort of the simplest quantum property of a black hole. But our baby wormholes, by definition, are in this sort of extreme quantum regime. They're as far away from classical general relativity as you can get and still talk about it as being gravity. So we're in exactly the regime that's interesting, where almost anything you study and any question you ask and anything you do is going to be getting at the real guts of quantum gravity, which is exactly what we want.
Daniel, is that the way you see it?
Yeah, I think that's a very nice point, which is, ultimately one might, first of all, be able to run experiments on quantum computers where wouldn't have been able to simulate the answer beforehand on a classical computer because it would have been too difficult. And it could be that the, answer to some question that could be measured on a quantum computer will teach us something about gravity in a very quantum regime, because, as Joe said, these are small wormholes. That means that they have very high curvature. So they're, only a few emergent Planck scale sizes. So that's sort of the sense in which it's like a a very narrow filament of space.
Mhm, mhm.
And that's the part of gravity that we don't fully understand yet. So we kind of understood enough to be able to know that the thing we're talking about, that we know that the thing we're seeing should be described as a wormhole, but it may, it has many other properties beyond the, simplest ones that we have measured. And, some of those are things that we wouldn't know the answer to in the gravity side, and we could learn how to understand it. So
Mhm, mhm.
I think that's a very interesting direction.
The pathfinder to quantum gravity, huh?
Well, thank you, everybody. This has been a tremendous conversation, and just thanks for sharing with us.
I'll see you on the other side.
See you on the other side.
See you on the other side.
Okay. Okay, bye, you guys. Thank you, everybody.
Ciao,
Thank you.
ciao, ciao.
Bye.
Bye.
Bye, guys.
Bye.